So let's wait for a few seconds before we are live. All right, I guess we are live. So let me just quickly check my. Give me a sec. Dun, dun, dun. All right, I think we are live. We're good to go. So let me see. The chat is giving me a little bit of a trouble here. The widget loading. Let's go to talks, chat. All right. All right, that's great. So we are live on all the platforms. We're good to go. So today, I wanted to talk about embeddings, right, and what they are, how we are going to use them, and so on and so forth. But before we get on to embeddings, we have to talk about how computers essentially understand information, right? And for that, they are simply going to talk numbers. Computers do not talk information, and so we have to figure out a way how we represent those numbers onto a computer. And to do that, say for example, if you have text, so we then represent them as UTF-8 encoding. That's now, but before that, we used to have ASCII, and we wanted to make sure that we figured that whole world doesn't speak English, so we had to get up with other characters. And for a brief while, we had this whole craziness with like Windows code pages. I don't know if people are old enough to do this. This was crazy, and we used to have all these collations in databases as well, where we didn't agree on a string type, so we essentially would store certain bytes in different localization settings on different databases and so on and so forth. And all this is basically to determine how we store text, the language that we all speak as humans, characters and emojis even, and how do we store them onto a computer. And I mean, we did the similar thing for images. For images, we do it's basically the bitmap format, which is rasters. If you are talking about vectors, then we basically use a variant of XML and call it SVG. We have various compression schemes on it, and various ways to represent the information like PNG, JPG, so on and so forth. When it comes to audio, again, we have wave, which simply gets these amplitudes of these waves, frequencies, and things like that. We store those waveforms. Or we could also use, FLAC, MP3, all these different kind of formats. And all these are basically ways we represent information. And if you want to do something like a video, we use H.264 or VP8 or something similar to store all this information onto these onto computers. Now, the problem really is that these are simply encoding and decoding information. Like whatever you put in, you would get out. Yes, we can do different analysis on it as such, but then the computer never actually learns a representation of it, right? It doesn't kind of say, hey, this is what you wanted to store. This is basically a summary of this blog post, or this talks about machine learning. It doesn't understand those concepts, or it doesn't say, hey, this is a picture of a kid wearing a hat sitting on a bench eating ice cream, right? It doesn't understand those things. So in order to bring about those understandings, that's basically where embedding is. But before we talk about embedding, I wanted to talk a little bit about what tokenization is, right? So, and tokenization is basically where we take these information that we have and represent them in a bigger space. So, mostly I'm going to talk about text in this video. Maybe we'll talk a little bit about image and text together, but a little bit. But mostly, I would want to concern myself with text because most large language models are dealing with text. I mean, there are multimodal models, of course, that are coming up. We will talk about multimodality in a future video, but today we're just mostly going to talk about text. And the idea is that you can store text in different ways. And this is a really cool app that I came across called Tick Tokenizer. It kind of visualizes the tokenization that is done by OpenAI. You can also, I think they have other, yeah, this is all everything that the Tick token library supports. But there's also Google Sentence Piece and so on and so forth. So what does tokenization mean? So when you write a message like this, you are a helpful assistant. So let me choose a different tokenizer. Let's take this CL100K base. So this basically what it means that it converts pretty much everything that you write into 1 to 100,000 sort of like a token. So let's say you are a helpful assistant, because there's most prompts start with this. So, and if you see, pretty much every word basically becomes a token of its own. So like helpful has the ID of like 11,190. And then the assistant has 18,338, and then there's this end token, and then this is 220 is probably end of string or a separator, sort of like a token sentence separator. You can also say the user can't know the JWT token that will be, or we'll say that will be passed to you. Now, for some reason, it knows JWT here, which is pretty interesting. And JWT is seen as one token. Let's see if I can call it something else. Okay, yeah. So if you give it something that it may not have come across, like for example, auth weird token, so it kind of breaks it across. Like for example, it has definitely come across the word auth, and then it has come across underscore WE, and then IRD kind of like becomes its own token. And if you see here, it has also broken down that will be, and that will be to like two different tokens here, and so on and so forth. So this is essentially what tokenization is, where it actually takes in like the words that you send it, and then it breaks it apart, and most likely it breaks it apart like, this is like byte pairs or things like that, where it'll take a series of bytes, and then it'll say, hey, this is the most common occurrence or the most like amount of occurrences on it, and so I'm going to take all that and I'm going to turn it into one identifier, and I'm going to basically assign it a value, and so this will be there. So like this tokenizer has 100,000 such unique tokens that you can have. So when you're giving a text to a large language model, your dimensionality of the vector that you do would be 100,000. So let's look at as opposed to, say for example, if you don't have a tokenizer like this and you're basically using only ASCII as a tokenizer, and you're only saying that I'll take ASCII values, so essentially you would basically have like 127 characters. Is it? Yeah, 127 characters as individual characters as the size of your you know vocabulary, and then right, essentially those are the tokens that you would send in, and you can basically give it a number from 0 to 127, and you will one hot encode. And one hot encoding essentially means that so if you have so if I say, oh, my this thing is like I have like A, B, C, and D, E, F, and this is all the vocabulary that I have. And if I have a word like B, A, C, then I would basically represent it with the vector 0, 1, 0, 0, 0. There's another 0 here, and then like that. That basically say, hey, I want to. Then I will do like put another comma here, and then I'll do 0, sorry, 1, 0, 0, 0, 0, and then for C I'll do like 0, 0, 1, 0, 0, 0, and this is essentially how I would have my vector. Probably it'll be a two-dimensional array, or a vector of vectors sort of thing, and this is essentially how BAC will get targeted. So if you see here, this is pretty sparse, and if you have to break it by character level tokens, then you might have lesser tokens, but then it also makes it very difficult to come up with structures and meanings and things like that on that. And that is the reason why we have tokenizers either at word level or sometimes at sub-word levels, because if you want to support multiple languages, then it becomes difficult to actually kind of say, hey, this is English, so it has these 26 characters with different combinations, but then you also have something like Hindi or Tamil that I speak, and so on and so forth. And if you want to express ideas across these languages, then it becomes difficult, and so we come up with byte pair encodings and things like that, which also allow us to mix and match different languages and turn them into tokens. So essentially this is what tokenization is. And before I wanted to go to embedding, I wanted to cover tokenization, because with this is basically an encoding stream. So that means that if you give these tokens back, you can get back to this text. So far you can do 100% translation between the tokenized representation of whatever that you're I mean basically the string that you're giving, and the actual text, so you can go back and forth. But with embeddings, that is not the case. With embeddings, you cannot go back and forth between this. So embedding tries to build a representation of it. So in a typical OpenAI, sort of like an embedding, right? So if you use if you pass in this text to this, and this is the model, and this is the easiest way to generate embeddings, it's going to give you basically back an object like this. And this object, this embedding object, would have 1536 values. So essentially what it's doing is it's going to take in a vector of so for example, if you have 20 words, say for example 20 comma 100,000, because you would have 100,000 possible tokens, and your thing here, I think we had 20, was it, or how much, 23, right? So the goal of the embedding model is basically take this vector of 23 times 100,000, run it through some magic, which is the embedding model. So let me put a box here. So this is basically the model, and that is going to give me back a vector of basically 1536 elements, right? So it's just going to have one item of 1536 elements in it. So, and 1536 is basically 512 into 3. And so there is something to that 512 number, we'll come to it later. But so this is essentially how embedding model is works, and we are trying to understand this box, the embedding model box, and then try to do this. And before we get much deeper into this, I wanted to talk about why having this dense representation matters, and the path that we have taken so far. When we started doing this kind of like neural network processing and all that, I mean, the old school, I mean, I wouldn't say even neural network processing. When we started doing text analysis, right, and you say, oh, this is how we retrieve text and so on and so forth, we've always had different approaches. Say, for example, like TF-IDF, term frequency inverse document frequency identifiers, or even come up with different word level embedding models like GLOVE, Word2Vec, GenSim, so on and so forth, where we basically treat your entire corpus or your dictionary as like a bag of words. You put in all the words in there, and then you train a model which basically tries to figure out, oh, these words are related to each other, and so I will try to give them like spaces. One such really cool way of visualizing this thing is called the embedding projector. It's by TensorFlow. It allows you to basically map out like words in a 3D space and tries to get there. So this is a word vec of like 10,000 words. So word-vec essentially has more words in it, but this basically gives us like 10,000 words, but then they are in a 200 dimensional space. I know visualizing anything more than 3 dimensions is painful. So I think they have basically broken down, they've done sort of like a PCA, which is principal component analysis. And then they've tried to figure out, okay, what are the 3 primary components or 3 primary axes on which we would visualize this. And they've done this. Again, this is an approximation. This is meant for us to understand embedding. So let me say we want to do the word bank. Okay, and this basically tries to find the nearest neighbors once I click on it, and then you have all these words that are there. Now these are these 3 components, and it says PCA approximate. It's like it's the fastest results that we sampled for like 50,000 points and so on and so forth. The data is normalized by trying to shift this for this thing. But if you see here, there is a clear pattern. So let me also try to do a uniform manifold approximation, UMAP approximation, because I feel this would give us a better projection than PCA. Let's try to do this again. So this takes a while. Okay, yeah. So you have these banks, and so this is just a different way of visualizing same data, but the data is the same. So, but if you see here clearly, there is bank. Bank can essentially mean like financial institutions, banks, finance, exchange, dollar rates, and then you have these economic policies that are there. Economy, economist, strip, which is pretty weird, and then there's check all the way out here, and then you also have these really cool like bridge, canal, vest, and then you also have things like Gaza and terrorist and settlement, because I guess this is about the Middle Eastern conflict here, bilateral policy and all that is in this space. So as you can see, even though it's like a very rudimentary sort of like a visualization, you can clearly see this model has kind of like figured out a place for each one of these words, and they've put them here. Now the trouble with this model is exactly this problem, where the bank essentially means different things, and if a bank essentially, if we're talking about like the Gaza Bank and we are talking about international policy and all those kind of things there, the weight or the meaning for this bank has to is largely dependent on the context here rather than the word itself, right? So the word word doesn't stand on its own. It always has to have context on what comes before and after and so on and so forth. And that was one of the biggest problems with just a pure word level embedding sort of models like GLOVE, GenSim, or or word2vec in this case, right? That's a problem with these models. Now, what like OpenAI embeddings and things like that do is that they take the power of transformer, and they can give you know they can give attention to the whole sentence. So because now if they want to focus on the word token, they know that this token has to do something with auth weird, and the user cannot know, and so it actually comes up with embeddings, custom embeddings for you, that is in the context of the sentence, and not just like a global embedding that has been trained once and is fairly immutable, and it doesn't quite translate across domains. So that's essentially uh, what this is going to do. So now let's look at how we can work with this embedding. So let's see. So we'll use the embeddings API, and then we'll try to create these embeddings out of this and see how we go from there. Let me just give me 1 second. Yeah. So essentially, we can just do this. So let me try to go to our playground, and you'll see if we can get to the embeddings. Oh, you can't do the playground doesn't have this. That's interesting. Okay, so we'll just make an API call then. Just give me 1 second. I'm just going to get to my terminal, set some secrets up. Bear with me. So I'm just copying the OpenAI token onto this. All right, so we're back. So I copied the OpenAI key here. I have a simple embeddings model that's here. So let's start building that. So I'm going to use the async OpenAI runtime again. And let me get a bunch of these in there. So this has APIs for embedding as well. So that's what we're going to use. So let me get main.rs. I'll do a cargo add Tokyo and async OpenAI. And let me go to cargo.toml and add this. And then oops. Let me add Tokyo main to this, async this, and I'll do an ls. So this should work. So let's also use async OpenAI, and we'll get the so we'll get the embeddings model, and so we'll do the embeddings colon. So let's look at the API. So I do need the client, I suppose. Right, so this is good. I'm just going to disable Copilot for a bit, and I'll do an LSP restart, just so everything is like clean. And so OpenAI, the Copilot kind of hallucinates a bit. Let's create a client. So let's do a client new, and we'll also do a client dot. I think you can do an embeddings based on this thing. So let's see. So embeddings basically gives us something. It gives an embeddings object, and on embeddings we can do, I think, create, and then we do a create embedding request. Okay, embeddings dot create should be create embedding request build request args. Okay, default dot so we'll be using the text ADA, text embedding ADA. Was that the embedding model? So let me look at the. Yeah, this is the model we are going to use. We are going to use the text embedding ADA 002 model. We'll talk a little bit about why this model and what are the other options we have and so on and so forth in a bit. Bear with me, but I just wanted to get the get an example out here. So we have this model, and we'll also have an input. So should we do this? A unique identifier representing it? Okay, that doesn't matter. We just need to get the input, and I think this needs to be a string. And we'll say you are a helpful assistant, or we can actually embed anything. So let's just embed something a bit more interesting, not just the this thing, because we're not dealing with a tokenizer here. So let's see if I can embed a passage from the OpenAI documentation itself. Say, and we'll do this. Right. So, and we'll also make sure that's readable. I can also turn it into a raw string so that and we'll do a dot build on this. Dot build. This will create a result object. I'm going to unwrap that and pass that into create, and I'm going to try awaiting that. I think. Yeah, I think create gives me back a result of a. That's interesting. So this is an async event. Yeah. So I think we'll have to do an await and then do an unwrap on this. So this will be the result, and we can look at. So result is basically the embedding response, and this should have basically the data, which would be our embedding, right? So this will be this thing. So I'm just going to print this. This is going to be an insane amount of data, but let's see what it looks like. And we'll put in data in here. So this is a vec. So I'm wondering it doesn't implement display. So we'll do a debug print. All right. So this is there. So this should be good. We don't need that. All right, so let's try building this and see what happens. Cargo run. And this is the embedding. So the embedding is essentially a huge number So we have data, which is basically embedding. This has an embedding object in it that has this. So essentially, we should be able to do a dot. This thing on it. So let's see. So this is actually an embedding response. This is the vec of embedding. So we only get one embedding of 0 dot embedding. Basically, is a vec of f32. So we can actually try to find the length on this. And we could say, and you would see that this is about like 1536 elements. This number becomes important. So this is the length of the embedding, 1536. So when we are going to talk about vector databases soon, and then this length kind of becomes important because you need, when you create the space, you need to know what's the space that you're embedding in. So this is the easiest way of creating an embedding. So if you have your corpus of text that you want to pull down, either for sticking it in the context. Say, for example, if someone is asking a question on chat and you want to have the context that has the relevant information, then you can basically pre-process your knowledge base or the information that you have into paragraphs or even entire sections, because the model length for these is like 8,192 characters. So this is a pretty big context, right? So 8,000 words. I mean, so even if it's a subword sort of thing and it's close to about, say, 6,000 words, it is still quite a big number of words that you can put in. It's like 2 essays or something like that, the worth of content that can go into an embedding. And you can create an embedding object out of that, and you can use that in your prompt to kind of give the prompt more information about it. So that is the easiest way in which you can use an embedding, or that's like this. But then you can also have different other uses for embedding, right? So there is this massive text embedding leaderboard that's there. What this does is it kind of benchmarks different text embedding models on various different characteristics. So what can you use of embedding for? I mean, obvious thing that I showed is, that I talked about, is like retrieval augmented generation. So if someone asks a question in chat, then you want to basically look up the answer and just show it to them, right? Or have that in the context and then like decorate your prompt with something else, and then you can do this. The other semantic search is the easiest thing you can do. But then you can also do question answer or re-ranking different things, or you can help with summarization and so on and so forth. So different embeddings, you can tune them for different tasks. So I had at Tarka Labs, we built this thing called Kili, which is sorry if I can type. Which is a podcasting tool that we built, and there we used multilingual embeddings. So where you could say impact of AI on society. Let me keep right. And even though I search in English, it's going to bring me back results that are in French. Because I generated an embedding which is kind of would be the same if it were represented in French as well as in English. So the server is behind the AWS what do they call it? It's not Lambda, it's ECS, but Fargate. Yes, this is behind Fargate, so it's taking a while. We scale it down to 0 because it's just a demo, so it's taking a while to come up. Let's speak anytime now. Yes.
Je ne parle pas d'un scénario de fin du monde comme dans les films de science-fiction.
So when I searched for impact of AI on society, it kind of gives this is weird. Let me go back one and then come back. So yeah, so it basically gave us back
Ces avancées ont suscité pas mal de craintes. Je parle pas d'un scénario.
So this is the phrase that it gave. And so even though I searched for like impact of AI on society, and I didn't even quite spell it out that way and so on and so forth, it kind of like got me back to the right phrase here. And that's the power of embeddings, is that it actually brings an understanding to the dataset in question, more so than any of the other text retrieval techniques that we have worked for like before, right, as an industry. And that's what is really interesting about it. And you can have these embeddings in different ways to mean different things and so on and so forth. So MTab leaderboard basically takes these and then it tries to kind of rank these on different these different embeddings. So if you look at overall that's there, so you have so many different models that are there. And the text embedding ADA002 is still here, right? We don't know the model size that are there. It has 1536 characters. This is the sequence length, or 8192, and you can see it has one of the largest sequence lengths out there. And then it has the average number of data sets that they tested against for different values and so on and so forth, and the score that it receives on this, right? And if you see here, across averages, it's like 60.99, but for say certain kind of, like for example, pair classification, it performs well, re-ranking, it performs well, so on and so forth. So you have different models that you can have, and then each one kind of like has its own strengths to do that. So if you especially look at bytext mining, and if you see here, the this is the model that we used as a part of Kili, and you can see for different tokens, different kind of like bytext tokens, it has this kind of value. So you could choose the embedding model that works for you. And I think this is one of the rare cases I would say, hey, just don't rely on what OpenAI gives in terms of embeddings. Because this is like a sticky problem, right? Anytime you have to deal with data and databases, they kind of become sticky, right? And if you can generate this embeddings for your particular use case, you want to test them before you commit to generating an embedding for your entire data set, because it's a expensive affair. You need support for GPUs and things like that before you go through this. And even if you decide, oh, you're going to use the OpenAI embedding for that, even though it is fairly inexpensive when compared with, say, the other GPT-3 calls or GPT 3.5 or GPT-4 calls that you're going to make, it quickly adds up, because you have to keep maintaining this embeddings as you get fresh data, or if you want to do fresh things, you want to regenerate these embeddings depending on how you break them up and so on and so forth. So this is something that I feel you have to invest your time figuring out which embedding is right for you and use that particular embedding. Let's say, for example, if there are two sentences, and if you're doing like search kind of like use case, so you could use a search case based on so you could have a sentence, and then the users are searching for pretty much the same sentence, like how you do a Google search on it, right? So users who are used to kind of like Google search want to put in those kind of like sentences which are similar to what they would find in a corpus, and then you bring that corpus back. But then there are certain other users where you want like question answering use cases, where if you want someone to ask a question and then you want to get the answer as a result. So when you generate those two embeddings, you want the question and the answer to have a similar embedding, so that you would then find those two embeddings to be similar in that space, and that is essentially where different embedding models work. And I feel OpenAI hasn't published a model, so we don't know what this has, but the knowledge cutoff really isn't important for embedding models per se. You just need to figure out, you just need to figure out if that works for you, like if this is like a question answer pair or a sentence similarity and things like that. And I feel these OpenAI models are big enough that it should be able to specialize over both question and answer in a part of its model, as well as sentence similarity on a different part of its model, and it should still work. So yeah, that's essentially what I wanted to talk about in terms of visualization. But I did want to talk about one other cool clip, this thing. So let's see. So clip is an embedding which is pretty cool, because what it does is that it tries to connect text and images into its similar sort of like a representation. So let's see if I can pull in a clip visualizer. One second. Clip embedding. Yeah, let me. So I thought it's like a playground for clip embeddings. Let's see if I can find one. Yeah, I'm not able to find that, but for example, yeah, so clip is one of those models where this is like a really cool paper that's there. So what they did was they basically trained image ResNet, and then they also had a text-based transformer model, and they trained that to make sure that they both provided this. So there's this text encoder model, and then there's this image encoder. So both of them lead to an embedding that's there, and then they trained it in such a way that the representation of both of them are similar, right? To do this. And so if you use you can use this as a classifier and say, hey, these are dog images, or these are this thing, and so on and so forth. But in the opposite case, you can also use it as an place where you can do like predicting a particular token that is in there. So this is amazing, because now this is one of the cool things that happen where you could describe something as a prompt, and then you would get an image. So these kind of like clip embeddings were really cool, because it was used to train like diffusion models and things like that on this. So it was built on these kind of clip models. So that is the reason why I feel embedding is like a really cool space to be in. Especially I think embeddings are like the heroes of the whole LLM space, because yes, you have the generative capabilities of these LLMs, but then how do you stop them from hallucinating is to provide them context. And to provide context, you need and you obviously cannot take all of the world's information and stick them into the context. You need to give them, you only have limited context window for some of these. So you need to be able to use them, and bringing in this kind of like relevant information from like embedding searches and things like that into the context is so useful. And we'll be doing another video on retrieval augmented generation as well, and we'll talk about how that works. But before we go, I wanted to also talk about Qdrant and vector databases in general. Now, this is a vector database that I'm going to be using for Vivary, but you have different other vector databases as well. You have Pinecone, which is the most popular one out there, and then you also have VV8. That's another one as well. See, I misspelled it, I'm pretty sure. And then there's also Milvus, which is also pretty cool, and it's open source as well. So, so I mean, you just have to take your pick. And the reason I like Qdrant is because Qdrant is written in Rust. It's very straightforward. It doesn't quite bring in the rest of the tooling. For example, Milvus is amazing if you are going to operate it at scale. It plays very well with the Kubernetes ecosystem. It has a really cool API layer that's written in Go, and then you have the core, the database layer, and it's called Nowhere, and that's written in Rust. While Qdrant is entirely written in Rust, and it's also a fairly simple code base that I could understand when I read through that. So it kind of gives me the comfort that, hey, yes, I understand this. If there is something that I would need to look under the hood for me to understand or fix something, that this is not entirely alien, right? To do this, and most of these are using algorithms which are trying to find points in higher dimensional spaces. Again, this is not something that's new. I mean, we have been dealing with like geospaces and so on and so forth, and we have been trying to find out what's the efficient way to figure out a set of points given a particular point. It's like a classic computer science problems, and there are algorithms such as KD tree that's there, and there's also quad tree that was used by Google for finding its internal kind of like node, which has like 4 children, so on and so forth. So this is like these kind of structures were already used in, sorry, not KS tree, KD tree. These were kind of used already in computer science earlier to try to find out like space partitioning and how do you get to those efficient space partitions to find out where you are. There was also this earlier like geo libraries like S2 and things like that, which have been using these kind of like quick space partitioning trees to get there. And Facebook also had another one called Face, which was Facebook AI similarity search. That allowed like really quick search for embeddings and so on and so forth. But what has emerged as a leader in this space is HNSW, which is hierarchical navigable small words. Now, this is like the state-of-the-art algorithm that's used almost across all serious vector databases to do this. There's also a notable mention, PG Vector. And then there's also HNSWRS. So this is another one of the cases where vector databases is basically going to get either get embedded into existing databases like Postgres and things like that, or they're going to be a standalone sort of like a implementation. Again, jury's still out there. It's still pretty early. We don't know what's going to happen in this, but I'm leaning towards like separate sort of like a specialized server because I feel even though people talk about vector databases, there's a database of vector. I think of them as indexing servers. I think it's like the right approach or the right mindset to look at it. Imagine you had something like Elasticsearch or things like that. It's like a search index. It's very specific about the kind of memory it uses. I mean, the more memory you have, the quicker it be able to index it, and it's more specialized. So if you have something like Postgres versus Postgres, which does all of these things, like for example, you could do full text search in Postgres as well, and so on and so forth. And again, it stores it in memory. All that works. But then if you're a big enough organization and you're already operating a database and that has its own server and so on and so forth, it's actually more practical to run a separate server, which then your vector databases can use, and they can have different sort of these paging mechanisms, indexing mechanisms, so what have you, to get to these. So I feel having the vector database as a separate service kind of makes sense. And that's the reason I like Qdrant, is because it's lean, it's mean, and whenever something that's lean and simple, I mean, as you discover complexities along your use case, you have a way to improve them. So let's look at some documentation on this, how it works and so on and so forth. So that is the docs. Yeah, resource documentation. Again, this is like a very simple sort of like a setup. You can basically use Docker, set something up, and then the API is really, really simple. So it's using Python, but we'll in more or less the same. So the way you do it is basically this is the vector that you have. So when you create a collection, you have to basically say what is the size of it. 1 second, let's see. Yeah, so basically the size you have to mention. So if you're using the OpenAI embedding, basically you have to say your size is going to be like 1536. And again, this is one of the reasons why I feel smaller embeddings may win out over here. It's easier essentially, right? I mean, if you can, do you need all that dimensionality in your vectors? Is something that you need to see. So you basically choose the size here, and then you figure out what is the distance metric you want to do. Again, you can do like cosine distancing or like Euclidean distancing and so on and so forth. And most models, they also specify what's the metric that they need. For example, here in OpenAI embedding case, they say, hey, this has been trained for cosine distance separation. So we could say, let's see, text embedding. They say what's the loss function for this, and let's see. Yeah, so it says which distance function should I use. We recommend using the cosine similarity as a choice of distance function. Typically doesn't matter as much, and it says that OpenAI embeddings are normalized to length 1, which means that cosine similarity can be computed slightly fast just using a dot product. Cosine similarity in Euclidean distance will result in identical rankings. So again, it depends on the model that you're going to use. If you're using some other model, then I mean, most models now have been looking at cosine similarity, but some models may just use the Euclidean distance. So okay, I have to tell you what cosine similarity and Euclidean distance is. So say for example, if you take policy and economic here, we don't want to just try to find the distance between these 2 points like bilateral and policy. What we want to find out is what is the angle from the origin that they make. So are they close in an angular fashion between each other, right? So I think that's what we need to look at. Then obviously, because you're dealing with like an n-dimensional space, so it's not just the distance between the 2 points that we want to look at. We want to basically try to find out, hey, is it are they close to each other in this point, right? And that's what cosine similarity does. And you can simply do that with a dot product of these points, these two vectors, and we should be good. And that's pretty cool. So that's essentially the kind of similarity search you want to do. So let's go to Qdrant's documentation. So this distance dot basically says that, hey, you're going to be using the dot product, and so you'll be using cosine similarity for these. And once you add points to this vector, you can then search for this collection and then given a query vector, and you can say, give me these points, and then it will give you back those score points. What's also cool about it, if you notice, is that you're giving a payload here along with this. Now, this is similar to how Elasticsearch works as well, right? So you can basically, it's going to store the vector points, but then you can also give it some JSON information as payload, and then you can also index on it, and you can also filter on it, and so on and so forth. So it kind of maintains a secondary index of like inverted lookup values and things like that, so that it can you can further whittle those results down. So when you look at, so let's look at the API reference, and we look at the search that's there. So let's look at points, and we'll say we're going to search for points. So when you search for points, you can filter, and you can basically say, hey, it should, or it must satisfy these conditions. and it can basically talk about, hey, this needs to be match text or match values or match range or things like that. And this is pretty cool because now you also have an aspect of like a database to it, but it's only so far as to create this inverted lookup index for these points, which can then be used for either optimizing like which parts it needs to look at, and like maybe maintain a separate like a bitmap index for these points, and then like the quickly filter them out, or to do it post after the results have come out. Then you say, okay, get those points and then apply this filter on top of that, and then like stop giving this. So this means that if you basically say, hey, I have these match vectors, but then only get the vectors that are matching this particular user or a client or something like that, you can also apply these filters on this and then like get only those values. So that's that for searching and this thing. So this is fairly straightforward. All of the stuff, I mean, you can just uh, you can simply this is like using any other Elasticsearch or Redis or what have you. So it's pretty straightforward in like making a search operation, putting data in, getting data out, deleting data, and so on and so forth. That's pretty much it to Qdrant. Um, so yeah, with Vividy, I'm going to be using OpenAI embeddings for the most part, because I feel it's like a good general sort of like a embedding generator. I'm also looking at for the multimodality, I'm definitely looking at Clip as one of the embedding formats that's in there, so that we can do like searches on images and things like that. But for the most part, it's just going to be OpenAI embeddings. I do want to mention sBERT. So sBERT is the sentence, like I said, we use this for our training models, and they have this really cool visualization of this is the sBERT model, which is called the bi-encoder, and sBERT stands for like Siamese BERT networks, and BERT is like a pure encoder transformer model that's there. So and this is how it worked, right? So you basically go through two different layers between sentence A and sentence B, and then they try to find the cosine similarity and then do that. But in cross encoders, you basically use the same BERT model, and then you probably just append these tokens together with a sort of like a separated token, and then that basically then tries to just give a number between 0 and 1. Right, and to do these kind of things for sentence similarities and so on and so forth. So these are two different kind of like cross encoders and bi-encoders, and with cosine similarities and so on and so forth. So I feel the way you want to do it is you basically cut this network off for this thing, and then you just get the embedding from either one of these layers in there, and that's basically what the embedding layer is. So you basically pull just the U part or the V part of it, and when you're running inference, you'd only run this part of the network. So that's how the embedding model kind of works. So maybe in a future video, we'll go a little deeper and try to build our own sort of like an embedding model, just to kind of learn how it works and how like maybe sentence translations and things like that can work as well. So yeah, and if you like this kind of content, I mean, just subscribe. I'm live from time to time on LinkedIn and YouTube and Twitch. So all the things are here, here, right? So here is basically all the links in the video that you would see. Just make